point of view. Okay, and then the week after that, we have the presentation and the business model canvas, and we'll talk about that later, and so on and so forth. Okay. Regarding the midterm, does anyone have any questions or comments before we jump into the lecture? Okay, I guess not. So, so the hope is that we should have the graded solutions back to you, let's say by not next week, but the week after. So in about 2 weeks, let's say.
Okay.
Okay. And because the TA will grade them and I need to check them and so on. So it takes a little more time. But if you have any questions, of course, just email me. Okay, so let's begin. So today we're going to talk about statistical ray optics, and the entire lecture essentially is based on before I do that, based on this very important paper by Eli Jablanovic, which you can see here. It's called Statistical Ray Optics, and the basic principle, and I would recommend everyone read through it. It's actually not that hard to understand. It's relatively straightforward. But the basic idea is that geometrical optics deals and geometrical optics in general deals with lenses and very, very standard shapes, very conventional shapes, let's say spheres, curves, and things like that. But there was this need to really be able to analyze much more complicated shapes, like very random textured surfaces, as you will see today. And there was no theory to actually explain these, what happens in these kinds of shapes. And that's where this whole idea of statistical ray optics came about. So that's what we will talk about today. Okay, so in order to lay the groundwork for why we want to talk about this, we should revisit what you learned in great detail in the last class, which is the physics of solar cells. So the solar cell, of course, as we know now, is basically comprised of a semiconductor material with a p-n junction. So you have essentially a potential barrier between these two semiconductor materials. Photons come in, gets absorbed close to this potential barrier, creating, and the photons come in with the energy which is larger than the band gap of the material, and gets absorbed, creating electron-hole pairs or carriers that can move freely and create current. So the holes, for instance, get swept across the junction to this side and then collected through the circuit to drive a current. Right? Electrons get swept across this way, drive to the load, produce current. So the current multiplied by the voltage across the load is the power. So that's how you get energy, right? So you understand the physics. So we won't do this brainstorming, but from a very fundamental point of view, if we think about the system from an optics point of view, how can you improve it? Of course, you can think about many ways. We've talked about many of these ways along in the last few months. But one approach is how. So there are two things one can think of. One is, how do you make sure the right kind of light enters the system very, very efficiently, right? And when I say right kind of light, there are two things to think about. One is the energy of the photon has to be greater than the band gap, and we will talk about that issue in one of the subsequent lectures. The second thing is the fact that you may want to collect light from an area that's larger than the size of your semiconductor, because a semiconductor may be more expensive than the optic that you can use to collect. And this is the whole idea of concentration, which we will also talk about, and we've been talking about along the way. Okay. Now, on the other hand, once the light has entered into the system, can we do anything about it? That's the whole subject of the discussion today. In other words, once the light enters the system, could we do something to the system to enhance the absorption of light? Okay, and the whole idea of this is can be thought of as what's called light trapping. Okay? And you will actually have one more lecture about light trapping later on, which is a bit more detailed in terms of actual practical implementations from Nagel in 2 weeks, about 3 weeks actually. Okay, but that's the key idea. So once the light enters the system, could we do something to force the light to be trapped inside the system so the probability of it being absorbed goes up? Okay, and that's the whole idea we're trying to analyze. Or you can think about this as a geometrical optics for complex or random surfaces or shapes. Now, the motivation for this can be considered by looking at this video. So I'm going to play a video which we will probably speed up a little bit because it's a little long. But this is from a few years ago, which shows one of the highest efficiency solar modules available. Okay, and the technology hasn't changed drastically in the last few years. So I'm going to back and make sure you can.
Something very exciting here from a sun power perspective, and also something quite special from a record perspective. Can you give us an idea what you're announcing here at Intersolar?
So here at Intersolar, SunPower is launching the first commercially available 20% efficient solar module on the market. It is a solar module series that is 20% efficient, and it's really benchmarking a new area of solar technology, module technology in the market. This module is not only 20% efficient, it also features a power tolerance of 0% or +5. So whatever we deliver is at or above nameplate power of this module. And then additionally, the module can be installed with transformerless inverters. This is something that hasn't been possible before with our modules, which have been grounded on the positive side. Now our modules can be mounted with transformerless inverters, which is very important for all our residential installs.
Now, everyone claims very high efficiencies nowadays. Everyone's announcing they've got some kind of record efficiencies. Tell us a little bit about what verifications you have for this module.
I know there have been a lot of controversial press releases about who has the most efficient solar module in the market, and we have been independently proven that a lot, that our module is the highest efficient. But we recently also received the award from the Guinness Book of World Records that this module is the highest efficient in the market, and it's proven independently that it is the case.
Now, this module is going to be available when?
It is available now. We have it in production.
Okay, so we'll kind of stop here and talk about why is this module so efficient. Okay, it turns out, so it's important first of all to appreciate that this is a very big deal. It's just from a few years ago, but it was a big deal because to cross the 20% threshold is always kind of a very important goal. So the question then is to ask, how did they achieve that? Okay, that's kind of the key idea. And achieved it with a fairly complicated design strategy, and it involved many steps. But let's look at some of the key things. So they call this, by the way, this is more recent product name, Maxion Cell Technology. So this is one of those little panels, cells that are essentially tiled together to make a big panel. So first of all, there are no wires on top. You'll notice that they're completely black, which means there's nothing to block the light from coming in, which is very, very important, right? That's first. Second, and that's the silicon part. Second, they use a backside mirror, which is shown here, to reflect the light back up. So it allows the light to essentially bounce at least 2 times through the silicon. So it increases the probability of it being absorbed. Finally, they use these thick plated copper contacts at the back. So all the contacts are now at the back, and they are fairly thick to reduce sheet resistance and contact resistance. So all those parasitic losses are essentially drastically reduced. So very important engineering steps that went into this. Okay, there's one thing which you can't really see here because it's at the nanoscale, which is what we will focus on actually in today's lecture, which is the fact that if we zoom in to this surface of the silicon, you will see something which looks more like this. okay, you will see something which looks like a big, giant textured surface, big forest, really rough, okay? And this is the whole idea. This is one of the most important reasons why the efficiency is so high. So the idea here is that light comes in from the top, it scatters off this structure, it actually refracts into this high index silicon, but it actually refracts in a very randomized fashion. So, and it reflects on the bottom surface and essentially gets randomized and trapped within this slab of silicon. So this is silicon, and it gets absorbed here. And that's the whole idea. The contacts, as you can see, are in the back. There's the N contact, P contact, and an array of these. Okay, same as before. Now, the whole idea. Is there a question?
No.
Okay. So what we want to do is, if the question we want to answer is, if we have a structure like this, how do we actually study what's going on to the light? What happens to light as it passes through such a structure? Right now, our geometrical optics tools are not sufficient in order to be able to look at this and say, okay, what kind of structure should I put in? How much will I get an improvement, and so on? And that's this whole idea we want to talk about in terms of basics, okay? And this is the paper, Statistical Ray Optics, we just talked about. Okay, so the whole, the principle of how we analyze this is based on the second law of thermodynamics. So we'll start from a very basic thermodynamic concept. And the concept is basically, let's imagine our universe of blackbody radiations at some temperature. Okay, that's our universe. And into that universe, we place a textured object of refractive index n of x. And let's say that's textured, and then it reaches a thermodynamic equilibrium. It's a textured optical sheet bathed in a blackbody radiation at thermodynamic equilibrium. So, of course, thermodynamic equilibrium means that it's at the same temperature as the environment. So, and under thermodynamic equilibrium, you can actually calculate what is the energy density within this material, or how much electromagnetic energy is actually inside this material per unit volume. Okay, and this comes from quantum mechanics, so we won't actually go into the details of where it comes from, but that's the basic idea. So under thermal equilibrium, electromagnetic energy density, which is basically the energy per unit volume within this material, which can be a solar cell, for instance, is given by Planck's formula, which is given by U equals h bar omega divided by exponent of h bar omega by kt minus 1. Okay, that's of course, that's a Planck distribution multiplied by the unit volume that is being considered. So 2d capital omega k squared dk. K is the wave vector of the electromagnetic field divided by 2 by q. Okay, we don't need to know all this, but just know that the most important thing here, as we will come to, is the fact that the U is proportional to actually k squared, and in fact k cubed dimensionally because of this factor here. And k is the wave vector of the field is given by n omega over c, where omega is the angular frequency of the field. C is the speed of light. Omega is the angular frequency directly proportional to nu, the energy, as we know. Now, from the electromagnetic energy density, which is this U, we can calculate the intensity of light within this medium by simply multiplying the energy density by the group velocity of the mode of light. Again, we don't need to know where this comes from. This is a very important theorem which comes from, again, quantum electrodynamics. Not so important for us to know, but the fact know where it comes from, except the fact that the intensity can be calculated by the energy density multiplied by the group velocity of the mode, which is g. Group velocity of the mode is actually d omega over dk. So dk cancels out, and you plug those in, you get an expression like that. Okay. Now, the most important thing here for us to appreciate is that you will see this intensity I. Ignore everything else here because those are all constants, right? Omega is just the energy of the photon, h bar is a constant, temperature is fixed, k is just wavelength of light, frequency, 1 over lambda, so it's also fixed. Everything is fixed here. C is this constant. D omega is just the the steradians, and this small d omega is just the frequency. Now, the most important thing here is the I is directly proportional to n squared. N is our refractive index. Okay, so from that we can conclude some very an important conclusion is that the intensity within a medium in thermal equilibrium with a black body radiation is n squared times higher than its environment. Okay, it's a very important conclusion that comes simply from thermodynamics and quantum mechanics. Okay, in other words, if your universe is bathed in a black body radiation at some temperature T, and you put a material of refractive index n inside this universe and allow it to thermally reach an equilibrium, the intensity of light within this material is given by n squared times the intensity of light outside the material. Okay, that's kind of a profound and very important insight. It's not obvious why that is the case. You can prove this actually from statistical thermodynamics. But again, just to think about it for a second, it just means that simply by using a higher refractive index material, I can increase the intensity of the light inside that material compared to the outside. Okay, so that's pretty interesting and pretty profound and very useful, obviously. Okay, so moving on. Now we are going to make, so that's a very fundamental thing that we're going to use. Okay, so keep that in mind. The next thing we're going to use is an assumption. Okay, is an assumption that's called an ergodic assumption, which basically refers to the behavior of light rays when they are random, and it's called ergodic. Okay, this means that once the ray enters a medium, it forgets where and in which direction it came from. Essentially, it's a referencing statistical randomness, and this will become obvious soon. But the idea is, think about a medium such that light enters the medium, and once it has entered the medium, it gets completely randomized in terms of direction. Okay, which means that it doesn't know, it forgets the angle at which it came from. Which is not true, for instance, when you talk about refraction or reflection, because in refraction and reflection, there are very deterministic directions, right? So you come in at some angle, and you go out at another angle based on Snell's law. Here, what we are saying is that if you have enough randomness to the surface, you can make the assumption that there is no deterministic angle at which the ray will be after a few bounces within a structure, within a material. Okay, again, a kind of a little bit of an abstract assumption, but it'll become clearer in the next slides. So the way to think about it is as follows. Let's say you have a textured medium. The surface is textured here. Let's say you have collimated light coming in at a single angle. Okay, it undergoes refraction here, as shown. It undergoes, let's say, total internal reflection here, okay, because this has a higher index than the surroundings. And it undergoes, again, total internal reflection here. So the idea is that after a few of these reflections, the direction of this ray becomes indeterministic. In other words, it doesn't matter how you come in. After enough bounces, the ray will be completely random inside the medium. So the light will be completely randomized inside the medium. This is the whole idea of ergodic behavior. In fact, you can actually rigorously show that this is true as long as the rays forget their initial direction after one or two reflections, which is, of course, statistically averaged over a big illumination area. So imagine a big beam coming in, which is illuminating this whole area. You have to average over all these rays. So when you look at in all these rays in average, once they have refracted into the medium and bounced around due to total internal reflection, then the direction of the rays become completely randomized. Okay, it's a very important assumption, and we'll come back to assumption again and again in this lecture. But keep that in mind. So for now, we have laid down two fundamental principles we'll use. Number one is that if I have a material in thermal equilibrium with a black body radiation, the intensity inside the material is n squared times the intensity outside. And the second assumption, And that's a basic principle. The second thing is the assumption that when light enters a randomizing medium, it becomes completely random. So it exhibits ergodic behavior. Okay, two things so far. Now, let's introduce one other assumption. Is not an assumption, but just a brief fact, is that imagine a situation where light comes in, it goes through this textured medium, where the two surfaces are textured, but in the back, we have a white reflective surface. So incident light's coming in from one direction, okay, it refracts here, bounces around here, some of it gets refracted out. If it's outside this, outside the critical angle, then it gets reflected back and it gets bounced around again. So this white surface essentially allows the light to have an additional probability of being inside the medium. Okay, and this can be represented by a factor of 2. So in this situation, light gets an additional pass through the medium, and you can write the intensity as 2n squared times the intensity outside. So the intensity on the right-hand side is the intensity inside the material. The intensity on the left-hand side is the intensity out coming in from the incident angle. So it not only gets the n squared due to thermodynamics, it also gets a factor of 2 because of this reflective surface. Okay, and keep in mind, in one of the first slides I showed you of one of those very efficient cells, there was a reflective surface behind the silicon to essentially gain this extra factor of 2. Okay. Now, we're going to make some caveats before we go on. First of all, everything we're talking about for now is only true for very optically thick films, which means that the physical thickness of the film has to be greater than lambda over 2n, where lambda is the wavelength, n is the refractive index. And so far, we have ignored absorption. We will introduce absorption shortly, but for now, we're ignoring it. Okay. So what does this optically thick film mean? It's pretty easy to understand. Let's take an example. Let's take a wavelength of 1 micron, 1 micrometer, refractive index n equals 3.5 for silicon. What is the smallest thickness? This theory might be valid. Of course, you take 1 micron divided by 7, right? So 1 over 7 is about almost 0.1 something. So it's a little more than 100 nanometers. So that means if your thickness is larger than a few hundred nanometers, then this theory is reasonably valid. So that's pretty good. That means this theory is typically valid for most of the solar cells, which are usually more than a few hundred nanometers. The other important number, of course, to keep in mind is how much enhancement in intensity is possible. So this is basically this number here, 2n squared, right? And that's easy to calculate because we know n, 3.5. 3.5 times 3.5 is a little more than 10. Then you multiply that by 2. So let's see, let's just calculate that quickly. It turns out to be about 24.5. So that's a pretty significant increase in intensity. So just by the fact the silicon has a high refractive index of 3.5, and by putting a reflector behind it, we can get a 25 times increase in the intensity of light inside the silicon. So that's really, really good news, right? Because that really helps us to drastically increase the absorption probability. Now, one last note on the ergodic behavior. It's important to understand that ergodic behavior of light is very common. And the way to think about this is, let's think about very simple shapes. For instance, like a billiard table. So if you consider a rectangular billiards table as shown here, the number of angles that can be, so the billiard ball, let's say, falls like that. So here, for instance, you have one bounce with 2 rays, and you can get essentially one angle that's assessed. So, and then you can show that with the rectangular billiard table, you can access only 2 angles because of symmetry, no matter whichever way you come in. So for instance, you come in at a different angle here, you will get this incident angle, will be equal to that, and then you'll get the same incident angle, you'll get a second incident angle here, and so on. But you'll only get 2 angles at most. So the basic point is that most simple, very symmetric shapes are not ergodic. Like a circle is not ergodic. But if you have any little bit of randomization, so instead of having a rectangular billiard table, let's say you had a polygonal billiard table, ergodic behavior happens very quickly. So for instance, we have a triangle here. The light bounces around very, very quickly. This is showing the light essentially reflecting around and giving you randomized behavior. In a square like this, it's very regular, so there's no randomization here. So this is not ergodic. If you have a pentagon like that, it becomes ergodic. As you can see, it becomes randomized. Of course, there are differences between light and billiard balls. For instance, light undergoes total internal reflection, which means that sometimes it can escape the system, right, if the angle is less than the critical angle. So our systems are not closed. So light can escape if the angle is smaller than the critical angle. So that's an important distinction. So we have to be careful about that as well. So with all these basic insights in place, now we're going to apply some mathematics to understand quantitatively, okay, what is the improvement that one can hope to achieve by using these texturing of the silicon cells. Okay. We talked about the escape cone, and just to quantify this a little bit better, let's make sure you understand. So the escape cone, for instance, can be thought of from a emission point of view. So in this particular case, let's say you have a photon, which is here, which is escaping from this point inside a high index material. If the direction of the propagation is less than this critical angle theta c, of course it will go into the air. If the direction of propagation is greater than theta c, it will get trapped into the surface mode. Same here, and the same thing here. If it can also get trapped, it can also get out of the system into the substrate. So since we know from Snell's law, sin theta c is 1 over n, the solid angle subtended by the escape cone is typically very small. So this solid angle here is roughly 1 over 2n squared times 4 pi. So that's a pretty small number because n is typically very large, as we know from before. This whole thing is like 25, right? So 4 pi over 25 is a very small number. So in other words, the probability that a light ray inside the medium will escape is typically small as long as the refractive index is high. Or in other words, another way to think about it is that a small amount of randomness is only required to create ergodic behavior. So with even just a tiny bit of random texturing, we can get ergodic behavior very, very quickly because very little of the light actually escapes. You only need a little bit of angular randomness in order to trap the light. This will become obvious also as we go on. So to analyze the systems, we consider geometry like this. So here we have an interface between the outside world and the material that we are considering, let's say silicon, and light is coming in, let's say straight down like that, with an intensity I incident. This is the normal to the point of that surface at which it's incident with an angle of phi, okay, and it refracts with an angle of theta. And we are considering a very small elemental area here, dA. The critical angle is marked here, theta c. So the light comes in, it refracts in. And this can also be thought of as a loss cone. Okay. A fraction of the light, T incident phi, will first be transmitted into the system. Okay. This transmitted light, so whatever is transmitted into the system, must be balanced by the light that escapes the system, because this is under thermal equilibrium. Okay, and we are going to apply this principle, which is referred to as detail balance. So it's very simple. It's essentially conservation of energy. In other words, the amount of light that enters the system should equal the amount of light that leaves the system, because the temperature of the system is remaining constant. It's steady state. Okay, it's in equilibrium. Okay, so we're going to apply that principle mathematically. So let's try to go through this carefully here. First of all, we make the assumption that the internal intensity is isotropic and is given by this expression. So this is the intensity inside this material. Okay. It is given by an integral over angles. Okay, so cos theta d omega, this is an integral over a solid angle d omega, okay, over all the solid angles of interest. And B internal is the internal intensity per unit internal solid angle, as marked here. So this is basically a way to figure out what is the intensity per unit direction of propagation, or direction of the solid angle. Okay, and the assumption is that is basically uniform because the intensity is isotropic. In other words, in whatever direction you look, that intensity is the same. So that's why we use that metric for this integral. And this is constant, so this comes out of the integral, as we will see later on. So we also added a factor of 2 because of the extra pass due to the reflective back surface. So that's that factor of 2. Now, the solid angle is then converted into d theta, which is this angle here, okay, the 2D angle, by simply going from d omega is sine theta d theta, and then the integral becomes from 0 to pi over 2, okay, 0 to 90 degrees, right? B goes out of the integral, then it simply becomes an integral of cos theta sine theta d theta, which is very simple to do. It's just sine 2 theta over 2, and you can do this integral yourself, and you simply get a half. Okay, and you get a very, very simple expression here. The internal intensity is 2 pi times the internal intensity per unit solid angle. Okay, so that's what's the intensity inside. Now, the intensity of light that escapes, which is going out through the escape cone, is the same integral here without the 2. Okay, so now we don't have to worry about the 2 because there's no back reflection after it escaped. And secondly, the integral is now done over the critical angle, not the full line, 90 degrees. Okay, so you go from 0 to theta c. Otherwise, the integral is basically the same. It looks a little bit different, as we'll talk about, but basically the same. Cos theta, sin theta, d theta. This part is the same. This part here is basically in internal intensity divided by 2 pi times t escape as a function of theta. Now we'll see what this means in a second. This thing right here refers to the intensity, which is this, per unit solid angle that is escaping the system. Okay, and that can be written basically as the internal intensity multiplied by some probability averaged over all the angles within the escape cone that it will escape, which is, it's a probability number which is roughly will become 1, later on we'll see, divided by 2n squared. Okay, so when you do this integral, again, all of these things come out of the integral, where we assume that this t escape is averaged over all the angles. So it becomes a constant, comes out. This integral is pretty simple to do, and you get this expression. Okay, now what we're going to do, so now we know this is the intensity of light that escapes the system. This is the intensity of light inside the system, and then we know what's coming in, which is the incident intensity, and we're going to put detail balance to it. Okay, we'll apply detail balance. Light coming in should be equal to the light going out. The light coming in is the transmission efficiency coming into the system multiplied by the intensity, incident intensity. That should be equal to the inside intensity or internal intensity multiplied by the escape, right? So this is what we just calculated, how much is the intensity that escapes. So again, just to clarify, we are looking at this system here. So light coming in, light escaping. Just this interface here. Light coming in should match the light escaping. Light coming in is simply this intensity multiplied by the transmission. Light going out is simply this intensity multiplied by the probability of escape, which is t. What we calculated as t bar escape divided by 2n squared. So let's come back to that expression. Okay. And then we can plug in all the equations from the last slide and swap these around. You basically get the internal intensity is now 2n squared times this term here multiplied by the incident intensity. Now, This is a little bit different than what we saw before, because if you recall, what we saw before was that the internal intensity was simply 2n squared times the intensity outside. Okay, now we see an extra factor here, T incident divided by T bar escape, which seems to suggest that one can actually go larger than 2n squared. This factor suggests that one can exceed 2n squared. Okay. For a perfect black body isotropic radiation, this is 1, and then it comes back to the original factor, okay, original equation that we saw. But which is this 2n squared term incident. Now, all this is saying is that if you are careful about restricting your acceptance angle, as you would, for instance, in a CPC, you can actually exceed the intensity. It's possible, but only if you restrict the acceptance angle or the incident angle, and the brightness theorem still applies. Again, this is a little bit of a detail which is not so important for you, but just keep in mind that all of this is applicable also for the CPC that we've talked about so far. Okay, now we are going to take this basic theory that we have kind of understood and apply it to the case of light trapping. Okay, now what does light trapping mean, first of all? So it's easiest to understand by looking at these conceptual situations. First, let's take a very simple case where you have this uniform slab. Light comes in, it simply refracts and goes out. And the angle at which this goes out is the same as the angle at which comes in, and it's just displaced. This is exactly the problem we had in the midterm. Now, in this situation, of course, the light simply passes through the material by this much, and it has some probability that it will be absorbed, but that's basically it. Now, you can increase the probability by putting a reflective back surface, as shown here. So the light comes in, refracts, reflects off, and refracts out. So now it has two bounces. So this ray has bounced twice. So the probability of it being absorbed in here is twice as high as it was here. You can do even better by simply having a regular structure on the top surface. So in this case, it comes in, refracts this way, then totally internally reflects down, reflects back up because of this reflector, and then refracts out. So here again, you've increased the bounces a little bit. So that means your probability is a little bit higher than here because you are spending more time inside the medium. So it's a higher probability that it will be absorbed. You can go one step further by, instead of making a regular structure, you can make this completely random as shown here. So then the light comes in. On an average, you can show that this shows ergodic behavior. It refracts in, reflects out, total internal reflex again, reflects, and so on and so forth. And you get more passes here, which allows you to get higher probability absorption compared to this. And of course, eventually, you can also texturize both surfaces, the top and the bottom, and you can very clearly see light refracts in, bounces around more, total internal reflex, reflects here, and escapes. So even more bounces. So this is the progression that people were thinking about doing, and which they actually did in order to get high efficiency. Okay. Now the question we are interested in answering is, how do we analyze one of these situations, D or E? Okay. Oh, before we do that, these are examples of the textures that are very common in today's solar cells. So for instance, if you look at some of the high performance cells today, they, under a microscope, they look kind of like that or like that. This is more regular, but still somewhat random. This is much more random. That was silicon. So we should make a brief point about why use light trapping. One of the main reasons is that you can end up using thinner solar cell materials, which basically means that you're using less material, so it's cheaper. And because it's thinner, it can also be flexible. So it has some significant advantages. The other advantage is that thinner materials have higher quality in general because you can grow just a little bit of it. So you can have fewer defects, less carrier recombination losses, and so on. So you essentially get much higher efficiencies. This is something we will talk about in a little more detail in one of the subsequent lectures when we talk about light trapping in thin film solar cells. Here we're primarily talking about somewhat thicker solar cells. not really thin film. Okay, so the last point we have to discuss is the issue of absorption. So far we have basically ignored absorption. We have assumed that the material is basically just completely transparent, which is of course not the case. Like you want light to be absorbed. That's the whole purpose goal here. So the question we have to ask is, what happens when there is absorption? So then let's consider the case. So let's look at the input light. The input light is the intensity, incident intensity, multiplied by the transmission efficiency. But now we also add the area of the incident light. So this is the total power. Okay, intensity is of course watts per meter squared. This is just a probability, so it is unitless, and this is meter squared. So the whole thing now becomes watts. Our escape, a fraction of light that escapes, is given by the area over which it can escape, the intensity inside the material, the probability of escape divided by 2n squared. Of course, we calculated this as the escape intensity in a few slides ago, and we just multiplied by the area. That's it. Light is absorbed at the interface during the reflection, right? Because you can assume that there's some light that can be absorbed at the interface, so you have to account for that, and that can be computed by simply doing the same integral as before over angles from 0 to 90 degrees. So this is our favorite integral from before, cos theta sin theta d theta, which is basically integrating over all the solid angles multiplied by the intensity per unit solid angle, okay, which is what this expression is. Eta is simply a fractional absorption coefficient. A is the area, and I intensity is the internal intensity that we have talked about before. This integral is easy to do, and you get an expression like that. So that's the absorption at the interface. We should also be aware of light absorbed in the bulk. Okay, so the light that gets simply inside the material itself. And to compute that, you do an integral with alpha, which is the absorption coefficient, multiplied by the internal intensity divided by 2 pi, and all these volume element. You integrate over the volume inside the bulk and the solid angle. The solid angle integral is the same as before, so you do the same kind of thing. In fact, this simplifies a little bit because of the volume integral coupled with the d omega, but you get an expression which looks like that. Alpha, which is the absorption coefficient, L, which is the thickness that you're interested in. This is the internal intensity multiplied by the area of the incident light. And when you multiply it all out, you get something like that. 2 times alpha L. When you do the integral, you get something like that. 2 times alpha L I intensity A incident. Okay. Again, you can work through the simple calculus here, but the basic principle is that now we have 4 terms we need to think about. One is how much light is coming into the system, how much light is escaping the system, how much light is absorbed at the interface, how much light is absorbed in the bulk. Now, with these 4 things, we can apply detail balance. Okay, so let's try to do that. Light coming in should be equal to light going out. So this is the incident light coming in. This is the light escaping. This is the light absorbed at the interface. This is the light absorbed in the bulk. So 1, 2, 3 should be equal to the first term. Okay, this is conservation of energy, obviously, also called detail balance. From this very simple expression, we can now calculate what is the, in this case, we can calculate what is the incident intensity. So you get a simple expression like that. But keep in mind, our goal is to increase the absorption inside the solar cell, which is this last term here, right? Our goal is not to absorb at the interface, but we want to be absorbing inside the bulk of the solar cell, which is this term, 2 alpha L A incident I intensity. So we'll find an expression for that, which looks like this. Okay. Which is just simple algebra from these two equations. Now, what we want to think about is what is the efficiency of absorption? In other words, what fraction of the incoming light is absorbed inside the bulk? And we want to maximize that. That's kind of our goal for designing any of these structures, right? So let's look at the fraction, which is the numerator is basically this, how much energy, power is absorbed within the bulk. The denominator is how much power is coming in from the outside. So that's the absorption. This is the input. Okay, and then you get an expression which looks like that. It is very important to understand here. This is alpha L is of course absorption coefficient determined by the alpha is the absorption coefficient determined by the material properties. So silicon has some absorption coefficient. You can't really do much about it. L is thickness. Of course, you can increase it or decrease it. But keep in mind that you don't want to increase it too much because then the cell material becomes more expensive, heavy, and so on. You have some control over that based on how you design the system. Everything else is you have very little control because N is refractive index and all that. So we'll simplify this shortly. So let's make some simple assumptions. First of all, we'll make alpha is very, very small, let's say, because the absorption is small, which is typically the case for the indirect semiconductor like silicon. So weak absorption, silicon is an indirect bandgap semiconductor, alpha is small. We'll also assume that eta is small. This is basically eta, if you recall, is the absorption probability at the interface. And typically the interface, if the interface is of high quality, then we can assume that this is pretty small. This means the fractional absorption due to imperfect reflections, which is that the interface is small, this is the ideal case. Then we can also make the assumption that the probability of escape is equal to the probability of coming in. And that's a reasonable assumption because it's the same interface we're talking about. Whether it goes one way or the other way, the probability is roughly the same. So the maximum absorption enhancement under these assumptions can be shown as 2 times 2n squared. And you can do this yourself, but it's pretty simple. You just assume T incident is equal to T bar. A's are equal, so these cancels out. Let's see, alpha L is very small, so you take this to the bottom. Okay, that means this becomes 1, and these things cancel out. Then 2n squared comes to the top. So we essentially end up with, let's see, the eta is small, so you ignore that. So you end up with 2 times 2n squared because this 2n squared goes to the top. So it becomes 2n squared plus 1. Anyway, you can work it out. So basically, the key things we did, just remember, is alpha is very small, T bar and T are the same, A's are the same, they cancel out, and eta is very small, so this whole thing cancels out. And basically, you will see that the maximum value is 4n squared, and the extra 2 here is due to the averaging over all the angles. Okay, so that's a very important conclusion. So let me just repeat that. What it's saying is that by using a random texturing technique, you can actually increase the absorption up to, in bulk silicon, for instance, up to 4 times n squared, which is a pretty remarkable number. That's over 50, or almost 50. Right? N for silicon is about 3.5. You square it, that's about 10, let's say, a little over 40, let's say. So it's a pretty big impact. So in the paper, he goes on to do some experiments to prove this is indeed the case. So let's go through it fairly quickly. So in the experiment, they use what's called an integrating sphere. And the experiment is simple. You put a silicon wafer with a white surface, reflective surface behind it. Light is coming in from this side. And whatever is reflected back from the silicon is essentially absorbed by this integrating sphere. So this integrating sphere essentially absorbs whatever is reflected back. Okay, so if the reflected back is very high, that means very little is absorbed in the silicon. If the reflected back is very low, which means that a lot of light is absorbed in the silicon. So that's one way to see. So 1 minus what's reflected is what's absorbed. It's a way to think about it. And the actual experiment, they first put a polished side facing the light. So then it's like a perfect reflector. So you expect a lot of light to be reflected. And then on the other experiments, exactly the same, except that the rough surface is now facing the light. And what you will see is that the rough surface, of course, reflects a lot less light, as expected from our analysis so far. The rear surface can be either flat or textured, so that depends on the experiment. Reflected light is then measured by the integrating sphere. So these are the results. So this is the backscattered light as a function of wavelength. Okay. So first of all, this plot here, the solid line, is with the polished or flat side facing the light, and you can see that this is absorption inside the. This is reflected light, right? Because this is what's measured by the integrating sphere. So it's very, very high here, and then it goes very low once the energy goes below the band gap. So this is the wavelength is decreasing. The energy is increasing. Energy goes above the band gap, it gets absorbed. Now, this plot here is the same experiment, but with the rough surface, the textured surface. So you can see the textured surface, the absorption increased, because the signal in the integrating sphere decreased. You can also see that the absorption band edge also got redshifted, which is good, which means you're absorbing more photons. More of the wavelengths are absorbed now. The dashed lines are theory and the solid lines are experiment. So it has pretty good agreement. Okay. So one very simple, so that basically confirms the fact that by doing texturing, you can actually increase the absorption a silicon wafer, and you can use this to make better solar cells. Then the next question is, could you use techniques like this to make even cheaper solar cells, for instance? And one idea which is very, very interesting and that's proposed in the paper, something I'd like to discuss a little bit, is to use granular silicon sheets. So these are basically little microparticles of silicon, which are embedded in a polymer matrix like PMMA, polymethyl methacrylate, which is nothing other than plexiglass. So the idea here is that because this is rough intrinsically, incident light comes in, it gets trapped within the polymer, and it reaches the silicon and it's absorbed. And there's a white backing here for reflecting the light. So the example is silicon microspheres are embedded in PMMA. Light is trapped in silicon due to the higher refractive index, enhancing the absorption. So the idea here is that PMMA is much cheaper than silicon. So by using a very cheap PMMA, you can have a very large surface area, and small silicon granules allow you to use very, very cheap silicon to absorb the light. I mean, not cheap, but you can reduce the cost of the silicon by using very little silicon to absorb the light. The analysis in this situation is a little bit different than before, because you have 4 different things that are happening, and you can apply the detailed balance analysis just like before, and you can think about it in PMMA. So light is coming from air to PMMA, plus light going from silicon to PMMA should be equal to the light escaping from PMMA into air, plus the light escaping from PMMA into silicon. Then the equations are the same. It's just that you have an extra escape mechanism. Previously, remember, the escape was only into air. Here we also have escape into silicon. The equations are the same as before, except that now you have N2 and N3, right? N1 is air, N2 is PMMA, N3 is silicon. And you have the corresponding expression. So 1 is air, 2 is silicon, 3 is PMMA. Okay. Yeah, sorry, I messed up. So 2 is silicon. Now, once you apply this expression, you can apply the detail balance also in silicon. So in that case, light is going from air to silicon plus PMMA to silicon should match light going from silicon to air plus silicon to PMMA plus absorption in silicon, which is, of course, what we're trying to maximize. And the expression is here. It's very similar to before. And we can, into this expression, we can actually plug in some actual numbers to see what it actually means. The refractive index of silicon is 3.53, refractive index of PMMA N3 is 1.5. The transmission from air into silicon is about 0.96 with an anti-reflection coating, which we talked about before. The intensity of light inside the silicon now is given by this expression. Okay, I1 is the intensity of light inside the air. Remember, 1 is air. So this is the transmitted light intensity. Now, alpha for silicon within the band gap of silicon is about 0. So you can ignore that. And then you get an expression I2 is that. So this is basically the same as saying 2n2 squared times I1, which is exactly the same as what we had before. So there's a different way to calculate the same thing and come back to the same conclusion. The intensity inside the silicon granules is 2 times its refractive index squared times the intensity in the air. Okay, this is actually exactly the very first thing we started with. Okay, so and then they also do some experiments to prove this is the case, and the experiment is the same. Basically, they place this silicon granules embedded in PMMA into the integrating sphere. So if you don't use the silicon granules, then everything is reflected back. So you basically get 100% of the light reflected back. With the silicon granules, you get much less light reflected back because you're absorbing this much light. So it shows there's a pretty significant effect. Again, this is a function of wavelength. Also, this is really interesting because this goes almost to the band edge of silicon here. It starts absorbing. Okay, so that brings me to the end of this part of the lecture, and I just want to summarize a few things. So the most important thing, so that we went through lots of concepts here, but the most important things I want you to remember are by using randomized texturing of the interface between silicon and air and using a reflective back reflector, you can increase the absorption efficiency, the absorption of light within a solar cell by a pretty large amount, like 2n squared, and that has a pretty dramatic effect on the total efficiency of the solar cell. Okay, that's kind of the conclusion of this whole lecture. But there are some details which is useful to understand, and one of the important principles or methods to that you should appreciate from this lecture is the idea of detail balance, which is essentially conservation of energy. Light coming into a system should match the light going out of the system. Okay. Okay. So with that, I want to talk briefly about the presentation, which is on November 9th. And if you have any questions, I can address it, but let's go through this first. So first of all, this is your second presentation, and the idea is to make a technical case for innovation. For this, you need to really have some detailed, I would say as much as possible, quantitative simulations or calculations. Hopefully, so you have some numerical simulations to back things up. If you have a prototype, please show measurements or videos from your prototype. If you want to bring your prototype, this is your opportunity. Or if you have a mock-up with detailed drawings, that's kind of the minimum I would say you should do. I would expect you to do a very simple cost-benefit analysis. In other words, figure out how much things cost, and if you want to add more complexity to a system, let's say a tracker, how much would that cost versus how much benefit does it provide in terms of total output of your system, let's say. In each of these cases above, you have to list your assumptions very clearly. Okay, now to help you do a very good job with the presentation, I provided you an assignment 4, which is due a week before, November 2nd. Okay. This is essentially a quantitative analysis of your system. I gave you a bit more detailed instructions. So I would say there are 5 things here. Evaluate the performance of your system in terms of overall efficiency. And that will be different for different teams, so you have to define them carefully about what that means. Number 2, summarize the main factors that determine the efficiency. What are the things that you can play with to adjust the efficiency? How does the efficiency or performance change with motion of the sun, whether it's daily or seasonal? And that may not be applicable to some of you, but if it is applicable, you need to do an analysis. I think it is actually applicable to all of you. Number 4, summarize the strategies to improve overall lifetime performance of the system. So in other words, over 25 years or whatever the lifetime performance is, how would you design the system to improve the performance, like make sure that it performs the same or as good as in year 10 as it does in year 1, for instance. If you have built a prototype, this is also a good time to summarize simple measurement results, and this should be all in a brief report. Okay, that's my last slide, so I'll stop here. We are a little early, and I can take some questions if there are any. If there are no questions, actually, let me wait. Are there any questions first?
No.
Okay, so then we will stop here, and then my suggestion is make sure you spend some time on assignment 4, because this will really help you do a good job on your presentation too, which is, of course, very, very important from your grade point of view. Okay, great. I'll stop here. Again, let me remind you, if you have any questions, feel free to email me or the TA. So for next week, next Tuesday, we have a guest lecture from the TVC, and next Thursday, we do not have a lecture. Just keep that in mind.